In this lesson, we're going to continue from where we ended. So I've got a couple of questions to help us understand some of the things that we've been talking about so far. Determining the number of moles or the mass, then determining the empirical formula in the normal case, and also determining the molecular formula, then as well as going back to combustion analysis, which is also a way of determining the empirical formula. Then basically we also need to understand the basic idea of the limiting reagent as the main concept for tonight. Okay, so before we get to look at these questions, I'd want to just do like a quick recap of the questions that are given in the story sheet. So question 1, for example, says determine the number in milligrams in 0.020 kilograms. So they're just trying to test your measurements. Okay, so you need to understand that 1,000 milligrams basically make up what? Make up a gram. Okay, so before we get to work with that, we need to convert the given kilograms to grams. And we understand that whenever you see a kilo, it means what? You multiply by 1,000 or 10 to the power 3. So you've already converted the given value to grams. So we've converted from kilogram to grams, and that's what we have. So now we also have the ratio of milligrams to grams. We can work with that now. So let me just try to move this to this side so that we are able to move. Okay, so looking at the ratio that we have, this can come this side, so we try to find the value of x this side. So we are saying if 1 gram gives us 1,000 milligrams, how many milligrams can give us those grams? Yeah, so if you don't know how to go about the measurements, make sure you watch the video that I made on the measurements so that you get to understand what basically these prefixes mean. So from there, if you cross and multiply, the answer that you are likely to get is basically going to be just 0.20 by 10 to the power 6. Okay, or in other terms, basically if you look at the value there, it's 0.020, so it will remain that 0.020 by 10 to the power 6, which you can also rewrite to be, so that can move, can come here, so 1 and 2, so then the power reduced by 2, sorry, so it will be 4. That is one way in which you can present your solution. Okay, so these are simple things that you can understand. So the units are in milligrams. Okay, then if you look at the, I think I can skip the second part. What you need to know is that 1,000 cubic meters basically make up what? Make up a liter. So in the question we have given you cubic centimeters, so you can just rate it to the ratio that you have. Then you'll be able to find what? You'll be able to find the value in liters of your x. Going to the third part of the question. For the third part, you've been given 325 grams, which is supposed to be added to 2.5 kilograms. So basically this requires you to convert the grams to kilograms. And how do you do that? You can divide by 1,000. So if you divide by 1,000, you're going to have 0.325 kilograms plus 2.5 kilograms. So you need to understand the rules that apply to significant figures. Whenever you're adding or subtracting decimal numbers, or let me just say numbers, in terms of addition and subtraction, you consider the least number of decimal places. So in this case, the least number of decimal places is 1 from the 2.5, because this one has got 3 decimal places, so we consider the least. So if we do our calculations there, we're going to have 2.825. So in terms of presenting our solution, we need to consider 2 decimal places. So the answer is going to be just 2.8 kilogram. Okay. Then another interesting question that I saw just from the first part, I did see a question that was requiring conversions from grams per milliliter. You need to convert to kilogram per liter. So what does this requires you to know? So this requires you to understand that the conversions from grams to kilograms. So we know that 1 kilogram basically gets to give you 1,000 grams. So if we are to convert, we need to make sure that we come up with a fraction of this in the way that the grams can go away. So we want to cancel out the grams. So we are supposed to multiply by 1 kilogram over what? 1,000 grams. In other terms, what we're just trying to do is we're dividing by what? 1,000 into the grams to convert it to what? To convert it to kilograms. Or if you want, you can just say, okay, I know I have 11.34 grams. Then I need to find the equivalent value in what? In kilograms. So, of course, if you cross out multiply again, you're going to divide 11.34 by 1,000. Okay. So at that point, you can cancel out the grams. Then you're going to remain with what? A kilogram per milliliter. So we don't want that to be our final solution, but we want to convert even the milliliters to liters. So basically, 1 liter basically is equivalent to 1,000 milliliters. Okay. So why is this true? If you look at a milli, it basically means 10 to the power negative 3. So if you multiply 1,000 by 10 to the power negative 3, it's the same as you're just like getting to divide by 1,000, which will basically be equivalent to 1 liter, which is true. So you need to understand what each prefix means, what it represents. So just a quick recap. So you need to understand when you have a dec, okay, when you have a dec. So for example, if you have decimeters, you need to understand that it's basically a 10 to the power negative 1. Okay, you multiply 10 to the power negative 1 by the units. If you have a centimeter, it's 10 to the power negative 2, which tells you that 1 meter is equal to 10 decimeters. 1 meter is equal to 100 centimeters. Then the next value is millimeters. So it's milli, it's coming from milli, which is just the one that I'm talking about. This is 10 to the power negative 3, which means that 1 meter is equivalent to 1,000 millimeters. So from there you go to micro. Okay. So for micro, what you need to understand is for micro it's 10 to the power negative 6. So micro is the same as 10 to the power negative 6. So 1 meter is equivalent to a million what? Micrometers. Okay. Then the other thing that is important is nano. Nano means 10 to the power negative 9. So it's basically 1 meter is equivalent to a billion what? To a billion nanometers. So these are the key negative prefixes that you need to understand. Then for the bigger ones, we basically just have a few. And in our study, we're going to focus more on kilo. Okay, so if you say 1 meter, or let's say 1 kilometer, kilo means 1,000, so we multiply by 10 to the power 3. Okay, then you also need to understand the mega. So 1 mega is different from milli because of a capital M. This one means a million, a positive value. Then we also have a giga. Giga is 1 by 10 to the power positive 9. So these are the bigger ones that we're going to be working with. So make sure you get to understand them and basically know how to work with them. So in this case, we want to convert milliliters to liters. What are we trying to say? So we're trying to say we have a 1 milliliter there. So a milliliter is basically equivalent to, so a milli we've said it's 10 to the power negative 3. So this is what we have as an equivalent value in terms of what? In terms of liters. So if you want, you can just remove the 1 milliliters and put this. Okay, now just trying to make it look better, what we can do is we need to understand that 1 liter itself is equivalent to 1,000 what? 1,000 milliliters. So we want to cancel out the milliliters, so we're going to multiply by 1,000 milliliters over liter. Every liter gives you 1,000 milliliters, so we are putting the milliliters so that they are able to cancel out as well. So the outstanding or the remaining units that are going to remain with we're going to remain with kilograms per what? Per liter. Those are going to be our final units. Okay, so we have, so 1,000 can also divide, so in this case the answer will not change. So checking your options that you're given in the question, that the solution is not basically there. So the actual value that you need to find is this. This is your answer for that question. Okay, let's try to move. So out of this, like on question 1, the other questions we'll get to do them in the tutorial that we can have next time. Okay, going back to the question that is under study now, we are asked to determine the mass of each of the following, where we have been given the 10.2 moles of ethane, 1.6 by 10 to the power negative 3 moles of sodium sulfate. So how basically do we get to determine the mass in such a case? What do we get to do it? So now, what we need to understand is that the number of moles are basically equivalent to what? It's mass over what? The molar mass. So this is a triangle that we came up with, which will help generate all the formulas that you're going to be working with. So number of moles are equivalent to mass over molar mass. So just from this equation, you can come up with all the equations that you want. So if you make the mass a subject, you cross and multiply. So it's basically the number of moles multiplied by what? The molar mass. So if you look at the question that we have, we've been given the number of moles, and they want us to find the mass. So the number of moles has been given. We can find the molar mass using our periodic table. Okay, so I can start with the first one. For A, we've been given 10.2 moles of ethane. So we've been given the moles, we need to determine the molar mass. So if you go to a periodic table, you're going to find that the molar mass of carbon, so the molar mass is basically the bigger value that you get to see on a nuclear notation. So what is an example of a nuclear notation of carbon? So the bigger value is what we are calling the mass number. So you multiply by the number of atoms in such a compound. So if you look at this compound, we have 2 carbon atoms. So I'm going to multiply the 2 by the 12.01. Then I'm going to add it by 6 multiplied by the molar mass of hydrogen, which is 1.008. So after doing your computations now, you're going to see that the value of the molar mass that you're going to have is 30.069. Okay, so grams per mole. What you have is your molar mass. So now we are saying you can determine the mass as a product of the number of moles by the what? The molar mass. So in this case, all we are going to do is just multiply the 10.2 moles multiply by what? The molar mass. So we are multiplying this. So it's grams per mole. I can even put it down there to show that we are dividing by a mole. So the mole can cancel out even. So the units that are going to remain with will be in grams. And the solution is going to be 306.7. So now, how do you get to come up with the units? You find a solution. You need to be very careful as you get to present your final solution. Look at the given data in the question. So if you look at the given information there, 10.2 has got 3 significant figures. So we're going to have 307 grams as our final solution. So feel free to pause and try out the second one just before you get to see the solution. Okay, I'm hoping you've tried it out. So equally, we need to determine the molar mass of sodium sulfate. So in this case, we are multiplying the number of atoms. In this case, we have got 2 sodium atoms. So the molar mass of sodium on a periodic table is 22.99 plus we only have a single sulfate. So sulfate or sulfur, sorry, has got a molar mass of 82.065 plus we have 4 oxygen atoms, and each oxygen atom has got a molar mass of 15.994. So basically, sodium sulfate ultimately is going to have a molar mass of 142.042. So that will be grams per what? Grams per mole. So we've come up with our molar mass. So we are saying our mass is going to be a product of the molar mass and the number of moles. So the number of moles has been given in the question to be 1.6 by 10 to the power negative 3. So we need to multiply this by the molar mass, which is 142.042. So our value is going to be 0.227267. So what do you think is going to be a final presentation of a solution? Look at the question. How many significant figures are we going to consider? So our solution is going to be 0.23 because we are looking at two significant figures in the value 1.6. So the value, we're looking at the first 2 values that are significant. So you check the next number, is it greater than 5 or equal to 5? If it is, you need to add a 1 to the preceding value. So that's how we have 0.23 grams. Okay, so I'm hoping you've understood. The next question says, determine the empirical formula. So this is what we talked about the other day, and we'll just shed more light so that we understand. So in a case where we've given you percentages, just consider them to be the masses. Okay, so determining the empirical formula requires you to find the number of moles of the given elements that consist, or that the given compound consists of. So in this case, we've been told our compound is only made up of carbon, hydrogen, and oxygen. So we're going to consider their percentages to be their masses. So for the first one, carbon is 40, hydrogen 6.7, 53.3 for the oxygen. So we are considering this to be our masses. So the molar mass, so remember we said our number of moles is given by the mass over the molar mass. Okay. So we're trying to determine the number of moles, so we can divide by the molar masses. The molar mass of the carbon is 12.01 grams per mole. Then the molar mass for hydrogen is 1.008 grams per mole. Then for oxygen, 15.9994 grams per mole. So avoid using the actual values, like the odd numbers, where you just say 12, 1, 16. They'll affect your solution, especially in a case where you have more atoms. So after doing your computations, what is 40 divided by 12.01? So what I'm getting is getting a value of 3.33. So I can consider four significant figures. Then for the other one, 6.7 divided by 1.008. I'm getting 6.647 moles. Then for oxygen, 53.3 divided by 15.9994. I'm getting 3.331 moles. So the basic idea is to divide by the least number of moles. So in this case, we're going to divide by the least. Which one is the least? So it's basically 3.31, right? So that we come up with a ratio. So you can clearly see that there it's a 1, there it's also a 1, because we are dividing actually by this exact value. 6.647 divided by 3.331 for the middle part, 6.647 divided by 3.331. Okay, so the actual value that I'm getting is 1.995. So 1.995 is just basically the same as, you can take it to a whole number, which is just be what? A 2. Okay, so there are going to be some special cases which we're going to talk about, where it is not possible for you to just like consider it, round it off just there and then. For example, in a case where you get to see, maybe you find the ratio of carbon to hydrogen to be maybe 1, maybe 2, maybe let's say 2.5. You can't just say this is 1, 2, 3. No, that is not okay. So in such a case, it is advisable to multiply it maybe by 10 or even double them, so that you have a 2, then you have a 5. Okay, but in a case where it is like 1.99, so it's reasonably just a 2 there. So in this case, our ratio or empirical formula is CH2 or, okay, so just for the sake of trying to see if you understand this formula, so what do you think is this representing? So this is like the empirical formula of a carbohydrate. So make sure you review your biology. Yeah. Okay, the next question is asking us to determine the molecular formula of a compound with an empirical formula of NH2. So what is important to understand is that the empirical formula basically helps us to find the molecular formula. So in a case where they've given you the empirical formula, like this one, all you have to do is write it in brackets, then multiply it by a known number of moles N equivalent to the molar mass. So the molar mass has been given to be 32.06 grams per mole. Okay. So now, what we need to understand is that the moment you just find the value of N, you multiply it by the empirical formula, then you'll be able to get your molecular formula, because the molecular formula gets to show the exact number of atoms. So the ratio should not change. Okay. So what happens if you go to our periodic table? What is the molar mass of nitrogen? What is the molar mass of nitrogen? Check your periodic table. So my periodic table says it's 14.00674 plus our hydrogen is basically 1.008. So this is like what we have multiplied by N should be equivalent to 32.06. So just a reminder, there may be some cases where you're given a question like this one, which requires you first of all to find the empirical formula. So then they ask you to find the molecular formula. So you just work with the empirical formula that you found, multiply it by N, then equate it to the given molar mass. Okay, not at all. So what do we have as our molar mass in this case? So basically our determined value is going to be 16.022 after adding what we have in brackets. N equal to 32.06. So at this point we can divide by 16. So what we're going to have is basically just a 2 as a whole number. So after finding your value of N there, you can now multiply with whatever you have in the brackets. Multiply against what? The empirical formula. So we have a single nitrogen, so we're going to have 2. Then we have 2 hydrogen atoms, so that body will be 4. So that is our molecular formula in this question. Question 20. On complete combustion, 0.246 grams of an organic compound gave 0.198 grams of carbon dioxide and 0.1014 grams of water. What is the ratio of carbon and hydrogen atoms in the compound? So just a quick recap on complete combustion. So what we need to understand, guys, is when you're talking about complete combustion, or just let me just say combustion analysis, because in this case we're talking about combustion analysis. Of course, complete combustion just tells you that the product is what? Carbon dioxide. Incomplete combustion, on the other hand, which you're going to talk about most in details as you get to talk about your organic chemistry, just produces carbon monoxide. Okay. So now, what is combustion analysis? So combustion analysis is a case where you get to determine the formula of a compound of a known formula. So you have a compound of which you know the elements that makes it up, but you basically don't know in what ratio they are. So you react that compound of a known formula but of known elements, you react it or you burn it in oxygen to give you carbon dioxide and water. So basically, under combustion analysis, you're going to be given a compound made up of carbon and hydrogen. Of course, it may have oxygen or even nitrogen or even just carbon and hydrogen. So now you need to apply the given concepts for you to be able to get to find your ratios. Yeah. So how basically do we get to do it? So in this question, we've been given the mass of a compound to be 0.246. Then we've been given the mass of carbon dioxide to be 0.198. Then we've also been given the mass of water to be 0.1014. Okay. So how do we get to go about it? So we need to understand that whenever you're trying to find a formula or a ratio, just like we did in the first part of the question, if you go back to the other question, just this one, we had to first of all come up with a mass. Of course, the mass, we consider the percentages to be our masses. Now, in this kind of a question, combustion analysis will help us to find the mass of the carbon, the hydrogen, and the oxygen. So, if you look at carbon dioxide, you need to come up with a ratio of the carbon in the carbon dioxide. So we only have a single atom of carbon in the carbon dioxide. Okay, so what is the ratio? So this ratio is supposed to be multiplied by the mass. It's like you're trying to find, it's like you're told in carbon dioxide there is 10% of what? Carbon. So you're trying to find the actual mass of carbon by multiplying the 10 over 100 by the actual mass. Now in this case we're using a ratio. It's like you're told 1 over 4. Then you're like, okay, let me try to figure out the actual mass of what? Of carbon. That's what we're trying to do. Okay, so what are we going to have? So we understand that where there's carbon there, we can put the molar mass, 12.01. Then we over the total. So we have 12.01 of carbon plus 2 multiplied by 15.99 for the oxygen as your molar mass, multiplied by the mass. Okay. So after doing your calculations there, what will be the mass of the carbon? So you have 12.01 over 12 plus what? Multiplied by 0.198. So I'm getting 0.0540342 grams as the mass for the carbon. So the same concept or the same principle gets to apply to hydrogen. So in this case it's a bit different because we have 2 hydrogen atoms. So I'll say H2 over the H2O. So we have 2 hydrogen atoms in a water molecule. So this will also be multiplied by the mass of the water that was produced. So we have 2 multiplied by 1.008 as the molar mass of hydrogen. Of course, even here we are supposed to divide by the total molar mass, multiplied by 0.1014. So from there, after doing your calculations, what you're going to have is your value for the hydrogen mass is basically 0.011347 grams. So we have carbon and what? And hydrogen as. So we've determined the masses of carbon and what? And hydrogen in the compound. So after that, these are the basic steps that you get to take. In a case where the compound is just made up of carbon and hydrogen, you can just end at this point. Now, there are some cases where, likely in this case, it is the case because we have, if you get to add the two masses, you're going to find that they are basically not adding up to the total mass of what? The compound. So it's likely that this compound also had what? Oxygen in place. So what do? So we'll say, okay, the summation of the carbon plus the hydrogen mass plus the mass of the oxygen should be able to give us a total, which is 0.246. So if you get to add, if you had carbon and hydrogen, which are these values, the mass that you're going to have is basically 0.065381. So that is our mass for what? The total mass of carbon and hydrogen added together. So now that we've added carbon and hydrogen, we can take it across the equal sign, and I can denote the oxygen by a value x. So we're going to have 0.246 being subtracted by the total mass of carbon and hydrogen. So that the remainder is going to represent what? It's going to represent the mass of the oxygen. Okay, so what do you get after subtracting 0.246 by 0.065381? So the value that I'm getting is 0.18062 grams. Okay, so now at this stage we've determined all the masses of the elements that the compound is made up of, and we can write them. Okay, so for carbon, in case you didn't take it down, for carbon the mass that we found is basically 0.246 grams. For hydrogen, the mass that we found is basically 0.011347. Then for oxygen, finally, what we found is 0.011. Sorry, I'll repeat that. For the oxygen, what we found is 0.18062 grams. So these are the masses that we have for carbon, hydrogen, and what? And oxygen in this case. So what do we get to do? How do we get to approach? So I'll repeat that. For carbon, for carbon, the actual value that we found is 0.05400342. Then for hydrogen, just as I've written it there. So now I want you to take it up from this stage where you've been given the masses. So it's like we are trying to solve this question where you've been given the masses. So we take it up from this stage, divide the molar masses, then come up with a ratio. I want you to come up with an empirical formula. Okay, then I can have a solution sent to the WhatsApp group. Okay. So now I want us to understand one important concept, which is the concept of the limiting reagent. Okay, of course this question may not be based on the same, but it's very cardinal that we get to understand the limiting reagent as we get to determine or solve questions that requires us to determine the yield or how much has been produced when given a chemical equation. Okay, so we need to understand that in a case where you have A plus B reacting in a chemical reaction to give us C plus D, okay, it's very, very important for us to understand that it's either A or B will finish faster. Okay, it's not mandatory that they're going to be finished at the same time. Of course, you may have the same masses reacting, but that doesn't mean that they are going to finish at the same time. Okay, so there are some things that affect that. All right, so now what we need to understand is that the reagent or the reactant that finishes faster before the other one finishes is what we call what? The limiting reagent. So I can give you a very good example of let's say you're trying to make zigolo or whatever you call it. Is it glucose? So you have sugar, you're trying to add it to water so that you come up with what? A test. So let's say you just have 2 kilograms of sugar, and you have a lot of, let's say maybe a 10,000 liters containers of water. So it doesn't mean that you're going to add the entire sugar in the water that you have. It's like your sugar is limiting you. So the sugar is like determining how much of water you're going to use to come up with your solution. So in this case, we can say that the sugar is what? The limiting what? Reagent. It is limiting how much of the glucose or the sugar that you can, that you can make or come up with. Okay. So that's the way we need to think about the limiting reagent. So whenever you've been given a question, for example, if you look at this question, we've been given the grams of that reactant and also the mass of the carbon monoxide, the other reactant. So now the question is asking you to determine the product, how much of the iodide was produced. So what is going to determine is the limiting reagent. So now, if you look at the question that we have, we don't know which one is the limiting reagent. So there are some basic steps that we get to take for us to be able to find what the limiting reagent. So we look at the stoichiometric coefficients, okay, and also determine the number of what? The number of moles. So let's try to get to do that. So if you look at this question, what have we been taught? We've been taught for the iodine, that compound there, it's 80 grams. 80 grams. Then for the carbon monoxide, we've been told it's basically 28 grams. Then for carbon dioxide, we don't know. Then for iodine, we also don't know. So how do you get to move them? So you can determine first of all the number of moles. So get to check your periodic table. You check the molar mass of the iodine, the molar mass of oxygen, carbon. Of course, carbon and oxygen, we are very confident and we know the molar mass of them. So what is the molar mass of iodine? Let me just try to check that out. Almost there. Okay. So we're trying to find first of all the number of moles by determining what? By determining the molar mass of what we have. So we have I2 for 5. Of course, we've been given the mass to be 80 grams. So now we need to determine what? We need to determine its molar mass. So that we're able to find the number of moles that we have in this case. So how many atoms of iodine do we have? We have 2. I'll write that. Then the atomic mass is basically 126.9 plus for 5 atoms of what? Of oxygen, which is 15.994. Okay. So 2 multiplied by 126.9 plus 5 multiplied by 15.9994. Okay. So what are we going to have there? What we're going to have is 333.797 grams per mole. So that's like our molar mass in such a case. So we do have our molar mass. How do we get to determine the number of moles? So determining the number of moles, basically, it's just going to be dividing the molar mass into what? Into the mass. So we have 333.797 grams per mole being divided into the 80. So remember we said our triangle is the number of moles is equal to the mass over what? The molar mass. So after doing our computations here, grab your calculator, 80 divided by that. I'm basically getting 0.2, I can just say 0.24 moles. because I'm getting 0.2396, so it's a 0.24 moles. Of course, it's advisable to, let me just try to use a better value. It's advisable to maybe work with 4 significant figures in your computations. So we have 0.2397 better off. So those are the number of moles that we have for the iodine 4 oxide. So I'll write that on top. So the number of moles that we have for that is 0.2397. That's what we've calculated. We can also do the same for the carbon monoxide. So carbon monoxide, what's the mass? The mass has been given to be 28. So 28 grams. What's the molar mass? So we just add like 12.01 added to 15.994. Okay, so what I'm getting is I'm getting something like 28.0094 grams per mole. Okay, so of course we're just adding 16 plus 12, which is relative to 28. So it's just like 28 divided by 12.0094. 28 divided by 28.0094. It's like just the one more that I'm getting. So now we need to understand that the stoichiometric coefficients are very, very important when it comes to our calculations. So in this case, if you look at the ratio of what we have, we do have iodine, of course, in relation to, we're trying to compare it with what? We're trying to compare it with, let me write it better. So take note, for carbon monoxide, we found one more. We've calculated one more. So I can write that. So for carbon monoxide, we found a mole. Okay. So now, we are saying, go back to the ratios. So if you go back to our equation there, comparing the iodine 4 oxide being compared to the carbon monoxide, these are in the ratio of what? These are in the ratio of 1 to 5. We're looking at the stoichiometric coefficients. So you can basically get any of the number of moles that you've calculated, either for this one or the carbon monoxide. In this case, I can go for the carbon monoxide since it's easier. So now, what are we trying to do? We're trying to find the number of moles that the carbon monoxide requires. We are saying we have one mole in the question. But then we are trying to determine how many moles of the iodine 4 oxide that the carbon monoxide requires. So if the value that we're going to find this side, let's say we get to find the 6. If you compare the 6 to what we have, it means that the one mole that we have didn't finish. Meaning that the iodine 4 oxide wasn't enough. But then if we get to find a lower value, let's say we find 0.1, that would tell us to say, okay, meaning that since we are 0.2, which is more than what is required by the carbon monoxide, that would mean that basically we add more than enough of what? The iodine 4 oxide, and that would mean that carbon monoxide is limiting. So let's try to find the value of x. So if you cross and multiplies, what you're going to have is 1 over 5. Because what we have is just 5x is equal to 1, which is just 1 over 5. And 1 over 5 is equivalent to 0.2. So we basically have like 0.2 moles exactly. Okay. So what does that mean? Compare the 0.2 moles that we've calculated with the actual value that we have in there. So we found 0.2. What does this mean? This means that 0.2 moles of iodine 4 oxide can react exactly with 1 mole of the carbon monoxide. So the 1 mole of the carbon monoxide is what we have in the question. Now this only requires about 0.2, but what basically was available is 0.23, meaning that it was more than what? More than enough. So which one is the limiting reagent? The limiting reagent is the carbon monoxide, because because it wasn't enough. Okay, we've seen that because only the one mole that is available for carbon monoxide can only react with 0.2, but since we have more than 0.2, the other reactant was more than enough, so carbon monoxide is the limiting reagent. So now, after determining the limiting reagent, you can go back to the coefficients now. You compare now the limiting reagent, which is carbon monoxide, being compared with what you are asked to calculate. So you are trying to calculate the iodine. So iodine 2. So what ratios are they in? So you need to check for the stoichiometric coefficients. For carbon monoxide, it's just a 5. For the iodine, there's just a 1 the other side. Okay. So now look at the number of moles that you have for the limiting reagent. So we had calculated the single mole. So now you may be asking a question again, why are we using the limiting reagent and not the other one? So we're using the limiting reagent because it's basically the one that is going to limit how much you come up with, because it's going to finish faster. And though you may have more than enough of the other reactant, provided the other one has finished, we can't have more of the products. That's the interpretation. So if you cross and multiply, you're going to have 5x is equal to a 1. And basically you're just going to have like 0.2 moles of what? 0.2 moles of iodine being produced. So now that you know the number of moles of iodine that are going to be produced, and you're able to determine the molar mass. Okay. So you know that a single iodine atom is basically 0.9. So you multiply by 2 because we have iodine 2. So what you get to have 126.9 multiplied by 2 is basically what? It's basically 253.8 grams per mole. Okay, so that's what you have there. So you found your molar mass, then you've also found the number of moles. You're able to find the mass. How do you find the mass? We say the mass is found as a product of mass and what? And the molar mass. Okay, so we have 0.2 being multiplied by 253.8. So what I'm getting after multiplying the 0.2 moles that we found by the 253.8, I'm getting a 50.76 grams. So what we have now is what? Is the mass of the iodine that was produced in the question. Okay, so that is how you get to work around with the basic idea of the limiting reagent. It's very, very important whenever they ask you to determine how much was produced in the question. So assuming they also ask us to find the mass of carbon dioxide produced. So in such a case, if you look at the ratios in that case will be 5 to 5, which is just 1 to 1. And that would mean that the number of moles of the carbon monoxide would be equivalent to the number of moles of what? To the number of moles of the carbon dioxide. So we just use the number of moles for carbon monoxide and the molar mass of carbon dioxide, then you'll be able to get the mass. So now, there is this question that I want you to work it out as your work. My solution will be posted, so make sure you work this question out. Okay, so in an experiment, 1.90 grams of NH3 reacts with that, which is a limiting reactant. So we are expecting you to find the limiting reactant. Of course, show your working. Then also trying out how many grams of excess remained. Then also how many grams of the nitrogen oxide is formed. So these are very simple questions that I want you to work out. And this marks the lesson for tonight, which is just basically based on determining the formulas and also just a quick recap on the measurements, then and also the limiting reagent more importantly. So in the next lesson, we're basically going to move a bit ahead and get to look at the things that we've left out, things that we've not talked about from, so that would require us to go to the issue of balancing chemical equations. Of course, using oxidation numbers, balancing using ion electron method. That will be the next lesson. And from there, then gets to concentration and molality. So thank you very much for watching. Feel free to share your questions to the group for guidance.